Hello everyone. In the previous class, we discussed about the stress distribution in case of the multiple openings. So today we will learn about the openings in laminated rocks. So first let us understand what do we mean by laminated rocks, and then we will see that how we can analyze the openings in such type of rocks. So here is a picture that gives us the idea about the laminated rocks. So basically laminated rocks are composed of succession of the parallel layers whose thickness is small as compared to span of the opening. So you can see here in this figure that there are various layers which are formed. So we call these as the laminated rocks. Now these layers, if you just take a close look, these layers are either unbounded or the bond strength between them is very small as compared to the tensile strength of the rock. So just one hammer is there. So this is just kept to give you the idea, the relative dimension of the layer thickness and its length. So basically these layers, say it is the one layer, this is second layer, third layer. So in between these two successive layers here you see, so the bond strength between them is very small, or sometimes they may be unbounded. So when we say that it is very small, so we compare it with the tensile strength of the rock. So it is smaller than the tensile strength of the rock. Now if an opening is excavated in such type of rocks which we are calling as laminated rocks, generally the roof is formed at a weakness plane and it is relatively smooth and flat because of the nature that there is either no binding between the two consecutive layers or it has very low strength. So due to the weak bonding between the laminae, roof rock will become detached either immediately or after some time from the overlying rock, and for a layer or number of layers which are loaded only by the self weight or the gravity. See, what happens is, let us say that these are the laminated layers. Now you make an opening here. So what happens is this roof, so there the layers are there. So the moment this opening is made, what can happen is that the roof can become, that is, this roof is what? Roof is this layer. So it may get detached from the overlying layers immediately or with respect to some time. Another property that can be there is that these layers, they will be loaded only by gravity, that is only because of their self weight. Now the detached layers, they are called as immediate roof and the overlying roof is called as the main roof. So you see that, let us say if this is the opening and you have these layers here. So the layer which is detached from the overlying rock, that we will call as the immediate roof. Now there can be only one layer in the immediate roof or there can be more number of layers in the immediate roof. So you see that the rock mass is huge, so there can be n number of layers. So it may happen that only 2 or 3 layers are getting detached from the overlying rock. So in that case only 2 or 3 layers will form the immediate roof and the overlying roof will be called as the main roof. Now in case of the laminated rock, there is going to be the heterogeneity and also the anisotropic situation. These laminated rocks, they are formed due to succession of layers. These layers can be either horizontal or it can be inclined, and therefore the stability of the excavation will partly governed by the direction of strike of the planes of lamina in relation to the strike direction of the excavation itself. When we talk in terms of the heterogeneity and anisotropy in rock, so that comes as two situations. First situation that can contribute towards this may be that each layer may be composed of the different rock types with different mechanical properties, because these layers they are forming because of the geological processes. So, they can be of different rock types depending upon the deposition over so many years. Another way that heterogeneity or anisotropy can be introduced, that will depend upon the orientation of the planes of lamination, because in that case the property can be different in different direction, or these can be direction dependent. So, let us take a look that how various type of the laminated rocks and the opening looks like. So, you can have the excavation in rock with the horizontal layers. Okay. So, let us say that there are few horizontal layers, and then maybe you have the excavation like this. So, you have here the ground surface, and various rock layers are there, maybe 1, 2, 3, 4, 5, 6, 7, 8 and so on. There can be any number. Now, their properties can be different, their thickness can be different, their elastic modulus can be different, unit weight can be different, and Poisson's ratio also can be different for all of these layers. So, let us say for this one maybe it is T8, E8, gamma 8 and mu 8. So, this we call as the excavation in the rock with horizontal layers. You can have excavation in rock with inclined layers. So, say let us say that this is what is the excavation, and you have this type of rock layers maybe. So, in this case again you can have the different properties. So, maybe say this is E1 mu 1, say this is E2 mu 2 and so on. And the orientation of the joint is say alpha. So, what kind of situation, this kind of sliding? Okay. So, this is excavation in rock with inclined layers. Or you can have a random situation. Let us say that here it is your ground surface, and then you have an opening here, say. So, maybe you can have different types of, let us say, the joint planes. Maybe here this is say alpha 1 and this is say alpha 2. So, this type of situation can also be there in the field. So, what we are going to see is that different types of situations are there, and of course, as I mentioned, then the stability of the excavation becomes the function of the orientation of these joint plane with respect to the orientation of the excavation itself. Now, what we have is the formation of a layer, or there can be number of layers which are loaded only by gravity. Now there is going to be two situations. We can have the detached layers, or we can have the overlying roof. Further, this detached layer is called as the immediate roof and overlying roof is called as main roof. I explained you that what exactly do we mean by detached layer and the overlying roof. Now, for both of these, the computation of the critical stresses or strain rates in main roof or side walls or floor of the excavation becomes the concern for us. So, when we say that we are trying to analyze the opening in the laminated rock, so basically we want to compute the critical stresses and the strain rates in main roof, side walls and floor. So, this is to be determined on the basis of single 2D or 3D openings in elastic or inelastic rocks. Now, the compressive strength of the laminated rocks having lamina planes normal to the direction of the applied stress, they are approximately equal to the compressive strength of non-laminated rocks. The reason for this is that the rock fails by shear across rather than along the plane of weakness, and therefore the failure on the side walls of a single opening in laminated rock, it should occur at approximately at the same critical compressive stress for an opening in the massive rock. Kindly keep this in mind, and therefore we can have the design equations as sigma t into factor of safety must be less than or equal to T naught, and sigma c into the factor of safety must be less than or equal to mod of C naught, and tau, which is the shear strength multiplied by factor of safety, must be equal to tau f, that is the shear strength. Now, this C naught is the compressive strength of laminated or non-laminated specimen of the rock from the opening. How to determine then the critical stresses in elastic rocks? These are done using the theory of gravity loaded clamped beams or plates. Now, which situation it is going to be beams, which situation it is going to be plates, that we will learn in a while. So, in the most general situation, you can have n number of layers or the strata in the roof portion of the excavation. Now, each of these layers, they may have their own thickness and mechanical properties. So, as I showed you earlier with the help of a figure, that their modulus of elasticity, their Poisson's ratio, they can be different from the neighboring layers, or they can have their own thickness. It is not necessary that all the layers they have the same thickness. Now, from the point of view of bending of beams in the roof portion and the relative thicknesses and mechanical properties of the individual layer, what will happen is that few layers above the excavation, immediately above the excavation, they may deflect together forming an immediate roof. The moment they deflect, they are going to have the separation from the overlying layers in the roof, and those we are calling as the main roof. Now, some of the above successive layers, they may form the main roof, resulting into the detachment or separation between the immediate and the main roof. Above the main roof, again there can be still some layers which may not participate in the process of deflection, and therefore they will be remaining intact. So, the design of underground excavations in the laminated rocks, it reduces to the estimation of span width such that critical stresses, they are less than the strength of the rock in the immediate roof, and also the critical strain rates, they are within the permissible limits. See, here I have shown you an excavation which has the span width of L and the length of the opening which is in the direction perpendicular to the plane of screen, that I am representing as B. So, in this case, this portion is called as roof and this portion is the side wall. So, here we are taking a particular case where all the layers are horizontal. So, only the horizontal layers that we are talking about. Now, if you have in the roof, two conditions can be there. When you have this L by B ratio more than 2:1, it will be treated by the theories related to flexure of beam. But in case if you have L by B less than 2:1, we need to use the flexure of plates. So, this is how, depending upon the size and the length of the excavation or the width and the length of the excavation, we need to decide whether there is going to be the applicability of the beam theory or plate theory while analyzing the openings in such laminated rocks. As I mentioned to you that we are going to use the theory of gravity loaded multiple beams or plates. How should we decide whether it is beam or plate? That also I discussed with you. It will depend upon the size of the excavation. Some of the assumptions which are involved with respect to this theory, these include that each beam has a uniform thickness and not the varying thickness. This means that, say this is the excavation and we have the thickness. That means that throughout the extent of the opening, the thickness of any layer is going to be uniform. You cannot have a situation like this. If this is the opening, let us say. So, basically you cannot have the situation like this. So, in this case you see the thickness of this layer is this much here and it is varying and became more here. So, this is really not allowed. So, this is the first assumption which is there. Then flexure of the beam or the plate is essentially due to gravity. That means that there are no external load, but only the self weight with which that these beams or the plates they are going to deflect. Now, each rock layer was considered to be homogeneous, linearly elastic and isotropic, and therefore, it precludes the possibility of any fracturing in roof layers. Although later on many research workers they have talked about the fracturing in roof layer, but that is the matter of the research. So, to start with, we are going to consider one of the very simple case where we are considering each rock layer to be homogeneous, linearly elastic and isotropic, and hence there is not going to be any possibility of any kind of fracturing in roof layers. Then the fourth assumption involves the ends of the beam or the plate, and it assumes that these ends are built in or encasted in the side walls because of the overburden or weight of the overlying layer. So, basically we are going to consider them as the fixed end beams or fixed end plates while making the analysis. So, we take few cases. So, to start with, we take the most simple case, that is when you have the single layer roof and it is horizontal. So, you see that how it looks like, how the geometry looks like. We have this as the excavation, this is the side wall and this is the roof, and there is only one layer here, single layer, and it has a thickness T. Now, this represents the case of the shallow excavation, and this situation can be there in case of the underground military bunker. So, how are we going to represent it when we have to analyze it? So, you see that I take this layer here in this particular form. So, this is the layer which has the opening width as the length of this beam. It has the thickness T, it has the flexural rigidity of EI, and it is subjected to a uniformly distributed load, that is Q. Now, what will be the magnitude of this Q? That will be the weight of this beam, because that is what is the assumption which is involved, that every layer is deflecting under gravity only, that is under its weight. Now, if you take 0 from here and you measure x from this end of the beam, you all know that how to analyze the fixed end beam subjected to uniformly distributed load. So, I am not going into the details of that. Let us try to take a look that how the deflections and other aspects are going to be. So, in this case, see, I is going to be 1 by 12 bt cube. B is the dimension in the direction perpendicular to the plane of screen. And what is Q? Which is gamma B into T. So, we have this equation, beam equation EI d4 delta dx4 to be equal to Q, and then you can apply the appropriate boundary conditions, such as delta is going to be 0 at x is equal to 0 and at x is equal to L, and the slope of deflected shape of the beam will also be equal to 0, that is d delta dx will be equal to 0 at x is equal to 0 and at x is equal to L. So, using these boundary condition, if you just solve these equation, what we get is the deflection as delta x to be equal to qx square upon 24 EI L minus x whole square. Then we have the bending moment, that is m is equal to minus q upon 12 6x square minus 6 lx plus L square. Then we have the shear force, which is represented by, say, capital V. So, that is going to be Q into L by 2 minus x. So, if we take the two location, that is one at the center of the beam and another at the end, which is the side walls. So, at the center, what delta is going to be? So, at the center your x is going to be L by 2. So, this will give you delta as Q L to the power 4 upon 384 EI, and in this case delta will be equal to 0, because that is what the boundary condition is. And the bending moment is going to be Q L square by 24, and in this case at the end it is going to be minus Q L square by 12. Similarly, the shear force at the center is going to be equal to 0, and at the side wall it is going to be Q L upon 2. Now, from the design point of view, we have to look at the maxima value, right. So, from the design point of view, we should be worried about the maxima values. So, what we have here as the delta max, that is going to be QL to the power 4 upon 384 EI, and if you just substitute Q equal to gamma times BT and I also as 1 by 12 BT cube, see what happens. Gamma BT L to the power 4 upon 384 E into 1 by 12 BT cube. So, what we are going to get is gamma L to the power 4 upon 32 E T square. And where this is going to be? This is going to be at the center of the beam. Likewise, we can have the shear stress, which I will write as V max, and this will be, or I write it like this. So, that is going to be, if you go through the theory of elasticity, basically it is 3V by 2A. So, it is 3V by 2A. So, 3 and then the shear you have seen, that was Q into L by 2. So, I just substitute it here, and then A is going to be your B into T. So, this is going to be again substitute this Q as gamma BT. So, that is 3 by 4 gamma BT L upon BT. So, this will get cancelled. So, ultimately you will get 3 gamma L upon 4. Now, coming to the normal stress, so we have, say I will marking it as sigma. So, what I have is M by I is equal to sigma upon y. This you know from the theory of elasticity only. So, the bending moment is Q L square by 12, and then you have 12 upon BT cube, which is I. So, here you have sigma, and in this case the neutral axis, that is going to be T by 2. So, from here if you just substitute Q as gamma BT and try to do try to simplify this, what you are going to get is sigma max is equal to gamma L square upon 2T. So, this can be tensile or it can be compressive. So, basically this tau max and your sigma max. So, basically this tau max and sigma max, they will be occurring at the ends or the side walls. Okay. So, if we just try to take a look here, that the shear stress in the side walls is proportional to the span width of the opening, and it is independent of the thickness of the roof layer. And the compressive or the tensile stress, which is the sigma value, that is the that is proportional to the square of the span width and inversely proportional to thickness of the roof layer. So, the shear strength of layers in the side walls in across direction, they are quite high, rocks being weak in tension. Ultimately, what we come here to, the design of the span width, and that would be governed by the equation for sigma z max. So, how do we determine this? So, this span width is going to be say L, that is going to be equal to square root of 2T upon gamma into sigma z max. You remember we obtained the expression for sigma max. So, from there I will find out what is the expression for L, or we can write this L to be equal to square root of 2T upon gamma into R naught upon Fs. Fs is the factor of safety and R naught is the modulus of rupture of the rock in roof layer. So, this is given by the outer fiber tensile strength. And of course, factor of safety is represented by Fs. So, here what we can do is we can consider various values of R naught upon Fs, and then we can try plotting the variation between the roof thickness, that is T, and the span width, which is L, but then we have to choose the appropriate scale. So, what we do is we work out the span width of the excavation as a function of thickness of roof for different values of this ratio R naught by Fs. And how do we plot it? See, we take here as log of span width on x axis, and on y axis we take log of roof thickness. And then we get this kind of set of lines. So, in this direction it is increasing value of R naught upon Fs. So, maybe you can have this R naught upon Fs, you can have maybe 75, 100, say 200, 400, 800 and so on. So, likewise you can develop this kind of chart. So, in case if you know that what is the roof thickness and corresponding to any value of R naught by Fs, you can use these chart to find out what is the span width. So, this is how the analysis of the single layer roof is carried out. So, here we discussed a very simple situation where you had only one layer in the roof which was participating in the deflection. But then you can have more number of layers, as I mentioned that you can have in general n number of layers. So, we will continue our discussion in the next class with the situation where you have two layers which are participating or which are the part of the immediate roof, and then we will extend that to the most general case where you can have n number of layers. Please keep that in mind that we will focus only on the horizontal layers for the time being, and then once we are done with these analysis portion, then maybe we can take a look at some cases related to the inclined layers as well. Thank you very much.